All right, so good afternoon, everybody. It's about 2 o'clock, so we are going to kick off this training here. I want to thank you all for joining us today for this presentation. Hope everyone's doing good out there, staying safe, staying healthy, and we're excited to share some really great educational content with you on high efficiency milling. My name is Jeff Rossio. I'm the digital marketing manager for Harvey Performance Company. So I'll be in the chat under the Harvey tool name. And if you guys haven't found the chat yet, that is going to be the best way to get in touch with us. The live chat should be on the right side of your screen or on the bottom of your screen on mobile. And that's going to be the best way to ask questions throughout. We have a few application engineers in the chat, Reese Trotter, Paul Fratto, and Adrian Hart. So if you see their names and they're answering questions, they are from Harvey Performance as well. If you have general questions for them, they'll help answer them throughout the presentation. And then at the end, we can dive into some more of the in-depth questions. So I've got Don Grandt, one of our national application engineers here on the line. He'll be delivering this presentation today. So with that being said, I'm going to pass it over to Don and we will get this thing started.
Thank you, Jeff, and good afternoon, everybody. How are you? My name is Don Grandt, and thanks for taking time out on this Thursday afternoon, morning, could be morning in some areas, but thanks for taking time out of your schedule to actually sit in with this presentation on boosting shop productivity by applying high efficiency milling techniques. First thing I wanted to kind of go over real quick here is it's a short introduction of myself. I mean, we do a lot of these trainings. This is number 2 in a series of 4 that we'll be doing in the next couple of weeks. But so a lot of people probably asking, what my experience is and what I have to offer. So I just kind of wanted to give a little background on myself. I've been doing this for 32 years, going on 33 years in the cutting tool industry. Had my own shop for several years. And the way we learn these techniques and the way we learn how to apply cutting tools, and I'm sure the way a lot of you have learned out in the field is by breaking tools, by running inefficiently in shops and stuff like that. So my experience comes from number 1, making cutting tools at the spindle, using cutting tools in my own shop, and then doing programming, testing, metallurgy, and all those types of things. So I'm going to give you a pretty high level overview, but we're going to keep it simple of high efficiency machining and what some of the problems and obstacles are going through that. So first of all, let's introduce, Jeff did a great job introducing us, but we're the Harvey Performance Company. So if you're not familiar with the Harvey Performance Company, we basically have 3 brands. We're out of Raleigh, Mass, is where our headquarters is. So you're probably familiar with Harvey Tool, which is one of our brands. Over 23,000 miniature tools, specialty cutting tools. Very popular, very good following on Instagram. If you don't follow us on Instagram, I advise you link up with us. Very good content. Helical Solutions is high performance end mills. This is kind of what we're going to talk about a little bit today. It's more going to fit a little bit more of the Helical Solutions. We are doing a micro machining one next week. So that one's going to incorporate a lot more of the Harvey tools. And then a recent acquire is Micro 100, which is basically your miniature and specialty turning tools. So we're going to actually get these series rolling and actually incorporate some of the turning side, Swiss, micro toolings, quick change, and stuff like that too. So these series are going to be very informative and hopefully help you guys out in your manufacturing. One thing I want to point out with this slide before we dive right into HEM and high efficiency machining is one thing we're very proud of with all 3 of these brands is all of them 100% manufactured right here in the US. Harvey Tools out of Raleigh, Massachusetts, Helical Solutions out of Gorham, Maine, and then Micro 100 is Meridian, Idaho. So we're a pretty proud team that we're all manufactured right here in the US, and let's keep it strong and going and running well. So let's dive right in. Okay, high efficiency machining. So what are we going to talk about today? First of all, we're gonna understand the top 5 current milling challenges. What are the challenges? Because those are what we have to overcome when we're looking at high efficiency machining. Then we're gonna understand what is high efficiency machining. Now, some people might understand and already know this and using paths and have an understanding, but we're gonna dive in a little bit of what makes it high efficiency and what are those little tips and tricks. Then we're gonna understand, oh, I'm going to say it. It's a nasty word, right? Chip thinning. We all hear the word chip thinning. Everybody throws it as chip thinning. Are you chip thinning? We're going to talk about chip thinning a little bit differently, and I won't be happy till you walk away from this meeting with not having a better understanding of what chip thinning is, because it has a huge part to do with high efficiency milling. TEA, which is tool engagement angle. All these things have to do with high efficiency milling. And then MRR, which is material removal rate. We're all trying to get the best material removal rate. We're going to talk about that. We're going to understand it. Then we're going to qualify an HEM application. It's kind of the close up. We're kind of going to run through everything we talked about, and then we're going to close with, how do we qualify an HEM application? Is it right for what I'm doing? So let's dive right in. Current milling challenges. So the first milling challenge that we all have, and whether you're an old school machinist or whether you're in a shop that maybe doesn't have certain capability, traditional tool paths have always been a problem for milling. They've always been an issue. A traditional tool path is basically going to take your end mill and put it in a horrible situation. It's going to put it in a situation that it doesn't like to be in. Not saying it won't do it, but there's new methods with the high efficiency machining that we're trying to overcome traditional tool paths. So in order to understand high efficiency machining, we have to understand what the problems and the challenges are with traditional tool paths. If you look at this slide that I've actually have up here, you can see every time in a traditional tool path that end mill hits one of those red areas, which is a parallel offset tool path, you have all kinds of problems. And there's so many things we have to do with a traditional tool path to combat those problems that it makes us inefficient. Doesn't mean we can't get through the job, but it makes us inefficient. So this, I guess you could say, is almost a two-part thing. If you're using traditional tool paths, you're going to understand a little bit better, hopefully, in this training to use traditional tool paths, but you're also going to understand how to overcome those obstacles. But when you hit those red corners, you get a lot of tool breakage. That's an option. You lose the corners of the end mill. You get chatter. You get a lot of chirping and stuff like that. Let's explain why this happens with a traditional tool path, and then tell you some of the cutting tools that you have to actually apply in these situations. So if we look at a traditional tool path and we blow this up, first thing is the first entry that your end mill has to make in a traditional tool path, whether you have a pre-existing hole that you've drilled or whether you're ramping down, the first cut you're going to make with that end mill is what? It's going to be a slotting pass, right? So you're actually starting to make a pocket here, and you're going to try and use speeds and feeds for a pocket or a peripheral cut. But the first cut you're actually making is a slot. It's a full slot. And if we use end mills and we understand end mills, when you use an end mill for a full slot, you have a lot of problems going on with those chips and the evacuation that we have to change things with the tool path. Let's run through this tool path a little. Say we clear this thing out. When we go to do a parallel offset, where we're running into the next path that we're going to make, which is a straight line, which is what we're trying to get to, we still have a full slotting condition, right? So now we're starting to run along our peripheral. The end mill's in a good spot. It likes it. It's feeling good. It's all happy until what? We start running into the corner. Now we're getting that engagement angle, and we're starting to run into the corner until we get into a full slot condition. Now I can tell you, like I said, I've had my own slot or shop for 10 years, and I programmed a lot of milling and learned a lot in my shop. When I would program a pocket, We would always program the end mill based on speeds and feeds that were recommended for the vendor. We would always look at this situation, or I would in most cases, and use the peripheral cutting speeds and feeds. Every time you use an end mill, the proper way to calculate speeds and feeds in your toolpath is by using worst case scenario. So if you're programming a traditional toolpath and you're having all these problems, you really need to program something like this in worst case scenario. So what you should be looking for is speeds and feeds of full slotting, right? Not peripheral cutting, not straight line cutting, not finishing, not light roughing, not semi-roughing, not even roughing. This condition right here should be programmed as a full slot condition because that's what the end mill's doing. And if you want it to last, that's how we have to program it. That's number one. What's going to happen when we do that and we program that in a full slot condition like that is number one, we're programming for full slotting. So we know that our feeds are going to be reduced. Our speeds are going to be reduced. So now we got to slow things down, right? Feeds and speeds because it's full slot and we got to be careful and we got to take care of that end mill. That's number one. Number two is we're limited on how much space we can have in the flutes because we're putting it in a full slot condition. And full slotting means large chips. It means you need a lot of room, a lot of chip evacuation. So now whether we're running in ferrous materials or non-ferrous materials, we're looking at 3 flutes, 4 flutes. That's about it. That's where we're going to be limited. So now we're limited on our flute count that we can actually use, which is going to reduce a lot of core strength and a lot of issues that we're trying to overcome. But these are problems. So when we're running a traditional toolpath, we have to kind of fit the end mill to the traditional toolpath. Even if you come from the outside of a part and you're doing an open pocket versus a closed pocket, what's the first pass we have to do? First pass is a full slotting condition. So what I'm trying to explain here is just get you to understand a little bit on a traditional toolpath that we are limited on how we can use that end mill in order to eliminate a lot of problems that are causing the end mill to fatigue and break down. So that's number one, is the toolpath has given us a lot of problems. Number two is of the milling challenges is the machine tools. We're limited by the machine tools we're actually using. Older school technology, older machines. Now understand, I'm going to get through this whole thing. I'm going to talk to you guys about a lot of things. I'm not saying, I will never say that you can't do it. And it's not a situation where you're not going to be productive in a shop by using old machine tools or traditional toolpaths. What I'm trying to get here is if you're using older technology, that you have to change things, right? We have to change. The only consistent or constant thing that we have to deal with in life is change, right? So we have to change things. So when we're running an older machine tool, first of all, we had limited processing speed. The processing speed or the look ahead for running high efficiency programs are going to be limited. Now, let me explain that a little bit. If we run a traditional toolpath like I showed you before, and we run through that, it might be 300, 400 lines of code, depending on how much you're actually running or material you're removing. If you run in an HEM or a high efficiency toolpath that we're going to dive into, those 3,000, 5,000 lines of code are going to turn into 10,000, 50,000, 150,000 lines of code, which if you're running older technology and the processing speed is going to be limited. Okay. Low rigidity. Rigidity has a lot to do with it, but not as much as you would think in HEM, because in high efficiency machining, as we get into that, we are limiting or we are reducing the pressures we're putting on the tool. That's part of the things we're actually helping. So you'll see a lot of people say, hey, you need that real rigid machine tool. I think, my opinion, right? Everything's served on opinion. I'm giving you guys opinions, but they're based on experience, okay? The experience opinion is if you're using older machine tools, you can use HEM depending on what you're trying to do. And because of the lower rigidity on the machine, you might have more success than running traditional tool paths. So the rigidity part out of it, we want as much rigidity in our machine tools as possible, but you're in good shape if you're using an HEM toolpath. We just have to sacrifice other things. Low horsepower spindles. There's another thing. We just did a training a little bit ago, and we're going to bring this up to the public and offer it on YouTube on exotic materials or heat resistant materials. Well, heat resistant materials right out of the bat, right out of the gate, are going to demand almost twice the horsepower as traditional materials, your 4140s. So if you're using a machine that has lower horsepower, it could limit some of the stress and things on your equipment where you have to change things. Remember, you have to change things and modify them. I put on here, RPM is not important. I want to make sure that everybody out there listening, because this used to be called, and still is called in some situations, high speed machining. We all know it as high speed. Well, believe it or not, HEM, high efficiency machining, in my opinion, takes the speed out of it, right? It's a path and a principle and an idea with the end mill where you're putting the end mill in a good situation. The speed is great if you need it, especially in aluminum and softer material. But RPM is not your deciding factor if you're wondering, hey, should I employ an HEM toolpath here or should I not? Do not look at RPM as an issue. We can help you through that. We got a support staff. We can talk you through that. You can run high efficiency machining on a proto track mill or a bed mill with a CNC. It's understanding the principles, how to use it, which we're going to train you, and then hopefully you have better understanding to do that. But we're more than willing to help you through that process too as well. Okay, the next challenge that we actually have is part fixturing. Part fixturing has a lot to do with it, especially when you get into super alloys, right? So you have rigidity issues, right? I put up this nice picture of fixturing that we kind of, have in our nightmares at home. These are kind of a worst case scenario, but we've seen fixtures like this, especially when you're running castings or you're running forgings and stuff like that. Sometimes you can't get the ideal fixturing, but fixturing is a big part of HEM and high efficiency. And this is a struggle that we all have with machine tool life, efficiencies, and trying to get the most out of your end mills. So we have rigidity issues, we have part movement, support, right? Support is a big one. As your material starts overhanging off your support beams, it actually wants to act as kind of like a diving board, literally like a diving board. The further you get away from the support, whether you're using a jack screw or out the end, it wants to vibrate and it wants to bounce up and down. Worst case scenario for running a carbide end mill. High speed, a little bit more, you can get away from it. But if you're using carbide and you're running that, you want to have as much rigidity as possible. Clearance is an issue, right? What is my clearance? What is my overhang? How big are my toe clamps? I want to get the most rigidity as possible out of my fixturing that I possibly can. Location, where is my material sitting on that fixture? That's very important. Stock to hold, what does it look like? I told you, is it a casting? Is it a forging? How do I need to hold that? And can I support it? And can I put something underneath it? The more rigid you can make your part, the better your tool life is going to be. This is all about tool life. End mills are not always cheap depending on what you're trying to get. And I'm here to tell you, getting the right end mill for material specific is the way to go. Getting that end mill, but what we need to do is we need to make sure the supporting cast for that end mill, which means your fixturing, your machine tools and everything else, is going to support it and make the end mill look really good. So it's very important not to just look at your $50 end mill when your fixturing was $5,000, your machine tools $180,000. All that stuff has to match up in order to get that end mill to really shine in your application. So let's talk about tool holder accuracy. There's another big one. The tool holder is what's holding your end mill. That has a lot to do with the accuracy and how the performance of your end mill is actually going to come out. So old technology holders, side lock holders, In some cases, it's time to look at nice precision collet systems, hydraulic chucks, shrink fit. If we can minimize the run out on the holder, we're going to minimize the force, the vibration, and everything on the tool, and it's going to give you better support, especially in HEM. Taper condition. What does my taper condition look like? Marring. Is there anything in the inside of the taper? Is there anything on the outside of my Cat 40, my HSK, that I can eliminate? Let's eliminate these issues. Pull stud. Let's make sure the pull stud's a good. There are some cheap pull studs out there. I'm sure we've all run into it. Let's get a really good pull stud. Make sure it's matched to the machine. Make sure it's in good shape. Make sure it's tight to the spindle. Excessive run out. We're trying to get less than 5/10 run out maximum. I say maximum. We do not want any more than 5/10 run out. Now, as your tool gets larger, you have a little bit of safety in there, but as the tool gets smaller, that's really, really critical. We run -5/10 grind on all of the tools that we send out. Most of it is industry standard, but you're really looking in a holder. You should be able to ask for 2/10 all day long. Most end mills, solid carbide end mills in a good holder will run out 2/10 all day long. Balanced holders. Now we're going to elevate RPMs and speeds and feeds, as you'll see as we jump into this next slide, which is HEM and stuff. You're going to see elevated speeds and feeds because of surface foot, and so you're going to want to make sure that your tool holder is balanced. Underutilized tooling. We're talking about that traditional tool path. That's it. So this is where we see the differences on how we can apply high efficiency to traditional tool paths. When we're running traditional tool paths, we're running those conservative speeds and feeds. It's underutilized tooling. We're buying this tooling, we're spending $50, $60, $70, $80, $100, $150. If we're getting up there, we're spending the money. Why use underutilized tooling? We have small axial depths of cut, but we have these huge radial depths of cut, as you saw in full slotting, and we have these long lengths of cut. This is kind of like buying an end mill or going to Subway, buying a 12-inch sub, eating 4 inches of the sub and throwing the rest in the garbage. Buy a 4-inch sub if that's what you want to eat. I'm full of these analogies, by the way. You'll see as we go through. So buy a 4-inch sub. Same thing with an end mill, right? If you only need to go down 1 inch with that end mill, and you're running a production environment, buy an end mill that's got a 1-inch length of cut. Don't buy an end mill that has 1.5 inches, a 2-inch length of cut, and then go down 1 inch. But then you're going to ask, well, wait a minute, Don, but I have all these tools in here and they demand different lengths of cut and all of that. And I like to use this one for that one. And I like to use this for that. Totally understand it. I told you I have my own shop. I get that. I understand it. But here's the thing I'm saying. If you're running in a production environment and you want to get the biggest bang out of your end mill and you're putting the least amount of cost into that, in that production environment, if you're only going down 1 inch, get a end mill that has a length of cut with 1 inch. Trust me, you will thank me, you will thank us, you will thank anybody. It will give you the biggest bang for the buck. So we're going to do small axial depths of cuts. That's the under and long lengths of cut. Not good. No corner radiuses. I see a lot of people that do these roughing strategies and they're roughing out the pocket and they don't put a corner radius on there. Poor tool life results in huge poor tool life. Unpredictable failure. This is the big thing. We want to get predictability out of the end mill, whether it be 2 pieces, 5 pieces, or 10 pieces. Predictability is the key. And when all these environments aren't matching up with the tool path, machine tools, the holder, unpredictability is huge. Deflection. Deflection is huge. And I'm not talking to deflection like when you were out at the bar and your wife catches you out somewhere else and you kind of deflect the situation. I'm talking about deflection of the end mill. Deflection of the end mill is basically how much that end mill is going to move and deflect on when you're cutting. And when you're running a traditional tool path, wow, I'll tell you, that deflection is all over the place. We want to minimize that. HEM is going to do that. High efficiency machining is going to reduce that deflection. Chatter. We want to reduce the chatter. Chatter is going to result in vibration. Vibration is going to result in low tool life. And then you're getting low MRR rates. So now let's get to the meat and potatoes. I know I just put down the whole background on this. I hope I didn't bore you guys with a $300,000 Makino. So what is high efficiency? These are going to take a lot of those issues that we talked about, and it's going to make them a lot easier to handle. So we came up with something called the 3 T's of HEM. Real simple. First thing is that we're going to talk about of the 3 T's is toolpath. Toolpath is critical. We showed you a traditional toolpath. Toolpath employs intelligent toolpaths generated by CAM, your computer-aided manufacturing software that strategically manages the cutting forces and maximizes productivity. The toolpath is key to HEM. A lot of these things I'm going to teach you, the toolpath, the software is going to take care of that. That's number one. Number two of the 3 T's is the tooling. The tooling, the end mill, we're going to utilize smaller end mills. I did say smaller. Smaller comes with a less cost. So we're going to get into that. Smaller end mills with a higher number of flutes, more flutes, which gives us a stronger core, stronger strength, less vibration, running at higher speeds and feeds. Last thing, most important, technique. Here's what we're going to do. We're going to employ light radial depths of cut, high axial depths of cut. So we're going to go all the way down. We're going to use that whole sub. We're going to eat the whole sub sandwich. We're going to use the whole length of cut that we bought, we purchased, we paid for. We want our money for it. We're going to employ chip thinning, which we're going to talk about, and we're going to control the angle of engagement. Basically, what we're going to do is we're going to make the end mill think it's, at the spa. We're going to make it feel great about how it's actually running in there. And see, spa is water, and water is good if you're not using high-speed steel. Carbide's not going to rust like that, so you're good to send your end mill to the spa as long as it's carbide or ceramic. But I wouldn't suggest high-speed steel, send it over there. Didn't mean to get on a tangent. So anyway, let's talk about the toolpath, right? The toolpath, intelligent toolpath. I showed you the toolpath before. This is an example of Fusion 360 Autodesk adaptive clearing. So you can see now we have a closed pocket on the one end and we have an open pocket on the other end. The toolpath, which is very important, is going to control the load and the forces on the end mill. So instead of it actually doing a full slot condition, in the slotting where it's a closed pocket, you can see we're going to circle interpolate down, which you can with an end mill. You can helical ramp down, and then we're going to circle interpolate out. So now we're going to keep the end mill engaged. It's going to be engaged constantly, but at a light radial depth and a heavy axial depth. And then we're going to pick out the corners. We're going to sweep in and then pick out those corners. That's an intelligent toolpath. Really simple way that I like, and remember I said the analogies, are telling you an analogy of how these toolpaths are. If you look at a traditional toolpath, it's no different than taking a car and driving it down a windy road in a mountain. That car has to slow down, has to hit the brakes. Forces on the car push it to one end as you take the turn, go up the hill, and then left and right, right? An intelligent toolpath or an HEM toolpath takes that windy road and makes it straight. So your car or the end mill thinks it's going in a straight line. That's really what the end mill is doing in these intelligent toolpaths. It's taking all these forces and it's making your end mill think it's going in a straight line. And when an end mill is just going in a straight line, what do? We get predictability. We get controlled forces on the end mill. So that's what we're trying to do. So the toolpath is key. So whether you're using a Mastercam or you're using an Esprit, and I'm plugging them all, guys, or whether you're using a solid cam or you're using HSM Works or Fusion 360, there are intelligent toolpaths within there that do all those calculations for you. So now, remember when I said that when you're doing a traditional toolpath, it's slotting, worst case scenario. So you're looking at using end mills with 2, 3, 4 flutes in roughing scenarios. Well, now, because we're going to take light radial depths of cut, and we're going to control and manage the chip, and we're going to manage the angle of engagement, guess what we get to do? We get to add flutes to the end mill. Now we can start using 5, 6, 7, 8, 9, 10, all of 12, 14. You really can add flutes to your end mill to get a stronger core and use the whole length to cut. So we're going to start using the whole length to cut. We're going to add flutes. So we're going to add core. We're going to add rigidity to the end mill. And that's the key. So now you might say, and this is where we dive into the weeds of it. Well, Don, so what is the right flute count for what I'm doing? I'm going to tell you right now the most important thing to selecting the right flute count for your application if you're using an HEM strategy. The most important thing to consider is what material am I recommended end mill to use. We're going to ask you, number one, what's the tool path you're using? And then number two, what material are you cutting? Because we want to make sure all chips break. They chip differently, stringy. So we want to make sure we give you the right flute count that's going to evacuate the chips. That's what the flute's there for, is evacuating these chips. So let's talk about the strategy. Let's talk about what's happening here. Let's dive into the things that are causing an end mill in a traditional tool path to be eliminated in a high efficiency tool path. Two things. There's actually three things, and I normally, when I do these things live, I get the audience's opinion of what they think the third thing is, because I only talk about two things. There's three things that are going to destroy an end mill's life quicker than anything, okay? Two of them that we're going to talk about is heat. Number one, heat will destroy and deteriorate an end mill's substrate and break through and reduce tool life. And vibration is number two. Heat and vibration are two of the big ones, right? We want to eliminate the heat. We want to eliminate the vibration. The third one that I kind of throw up there is called recutting chips. Recutting chips, especially in some super alloys, really going to destroy your end mill's life. So what we're trying to do with HEM strategies, and what HEM strategies have done, is they've taken heat and vibration and eliminated it with an HEM toolpath. Remember, going in a straight line. So where does the heat and vibration come from? Cut, and I have a slide coming up here that's going to show you that. We generate a lot of heat, okay? The vibration comes from, and this is going to be, and I told you, there's a series of these things we're trying to explain. So if you can jump on a few of these, it would be great for you to guys, for everybody to kind of put things together. The vibration comes from is because we're limited on our flute space, okay? And we're taking light axial depths. Axial depth means down vertically, or in Z. We're taking light axial depths. We only have 4 flutes, 3 flutes. So what you have is you have one flute in cut, and then that flute exits, and then another flute comes in cut. So what you get is you get a slapping effect on the end mill, because we're having one flute in cut, one out, and another one in. So when you have a slapping effect with the end mill, you get vibration. That's where the vibration's coming from. And that's where that end mill's slapping on there. And that's where we don't have a strong core, so we have vibration. So if you look at the picture on the right of your screen, what we're doing is eliminating the heat and the vibration. The heat is eliminated because we're going with a light radial depth of cut. That radial depth of cut, which is the side depth of cut, is going to a lighter radial. So instead of 60%, 50%, 70, 80, 100% radially or full slot, we're doing 4, 5, 6, 7%. So that means we're in the cut with those flutes for less time. So that's where we're eliminating the heat. Now, where's the vibration being eliminated? Our vibration is being eliminated because we're stabilizing the cutter. We're stabilizing the cutter 2 ways. Number one, we're stabilizing it because we're putting 2, 3, 4 flutes in cut at one time. So it doesn't get that slap back effect. Anybody that runs an end mill in a straight line in a path always notices when the end mill exits the material, you see a shaded line at the end of it, right? That's the end mill deflecting. And yes, carbide deflects. Trust me, very, very less than high-speed steel, but it will deflect. So what we do is when we stabilize the cutter, we put 3 flutes in there. We put the end mill under load. We stay in the tool path under load. That's what an HEM tool path does. We stabilize the cutter. It has less bouncing. It has less movement, less vibration. That's how we eliminate the vibration in the end mill. So we're taking away the heat. We're taking away the vibration. We're making that tool sing in there and make it feel really comfortable. So we have a lot better chip management. Let's talk about the heat and the heat zone. If you look all the way over on the right, you can see at a 50% radial step over, look at where we're at in that heat zone, right? That tool is in that heat zone for a lot longer. As we start changing that radial depth and changing the tool engagement angle, you can see where the heat zone gets smaller and the cool down zone gets greater. So now we're minimizing that heat all the way to the point, whereas when you have a light radial step over on the left-hand side, which you can see over there, our heat zone is very small, 8% angle of engagement. We're going to talk about it, angle of engagement, so don't worry if you're not fully understanding what the angle of engagement is, but that heat zone is a lot less. So where does this make sense? This is what I love to throw up with this slide, because all these trainings have different levels of experience, right? There's guys that know a lot of this stuff, and then there's ones that just want to learn a little bit more. So then you go, well, yeah, but where do I know how much to do the step over and the angle of engagement? This slide right here is very important to understand your material and how much your material pushes heat back into your end mill. Again, we're doing another presentation on the heat and the material. So real quick example on this, if you're running aluminum or 1018 or even a 4140 annealed, and I know those are ones that everybody's heard of, you can get away with a little bit more radial step over because we're not going to push as much heat back into the cutting tool. Now, when you're running Inconels and you're running Washballoys and you're running Hastelloys and you're running Renees and you're running all those, and trust me, the people that are on this training and are hearing those names are either cringing because they have those issues or have either figured out the recipe that we're talking about and have got it nailed down. Those are where you want to reduce those radial step overs, reduce that heat zone, let it cool down a little bit, and you're going to see an increase in your tool life. You're definitely going to see an increase in your tool life. Now, I know you're thinking productivity. How has this changed my productivity? We're getting there. Don't jump too far ahead. We're going to get into productivity. So let's talk about chip thinning. This is a big part of this, right? Chip thinning. Everybody's heard of what chip thinning is. I'm going to give you a definition of chip thinning, and then we're going to talk about this slide right here. Chip thinning's definition, and this is almost exact definition, is where an end mill steps over less than 50% of its diameter, example, half-inch tool. If your radial step over is less than 1/4 inch, it causes the chip to be formed to be less than what you programmed. Okay, so let's just go over that again. So if you step over less than 50% of the diameter of the tool, the chip or inch per tooth that you are putting into your program is not actually what the chip thickness is that's taking. Okay, so what we need to do is we need to compensate for that. Radial chip thinning is very important to maintaining. When end mill manufacturers send out the recommended chip thickness or inch per tooth, it is really based on what we feel that cutting edge with that rake, with that edge prep, with that geometry, with that flute depth, that's the chip thickness we need you to maintain to give you optimal performance. So if we're not achieving that at the spindle because we're chip thinning, you're going to have fatigue, you're going to have tool wear, it's not going to last as long. So what we need to do is we need to accommodate for chip thinning. Take a look at the slide here. If we're coming around with an end mill and we're programming 2 thou inch per tooth, that 2 thou is at 50% of the diameter. If we're only stepping over 10% of the diameter, guess what? 2 thou chip thickness just turned into maybe 1 thou 2/10. Got a lot smaller because we're actually not hitting that material where we actually need to get chip thickness. So how do we combat this? How do we combat chip thinning if I'm telling you to do all these thinner radial step overs? We feed it faster. Bingo, right? We get to feed it faster. If we take a look at this on chip thinning and we just look at this slide as heat, let's just look at this as heat, right? Our chip load programmed on both of these, left and right, the load is going to be the same if we compensate for chip thinning by feeding it faster. The load is going to be the same, so you're not hurting your end mill. But look at how long it's in the cut by the radial step over. So our load is the same at cut because we're trying to program the same chip thickness, but the load is a lot more drastic as far as on the right-hand side with a lighter radial depth of cut, and we're keeping it out of the heat zone. So we're going to maintain the same load. We're not changing the load or the chip thickness that we want on the end mill. What we're doing was we're stabilizing the cutter, we're keeping the load on there, and we want to maintain stabilization for, we take out the vibration on that. This is a real good slide for TEA and force. So that's a good segue to jump into TEA, which is tool engagement angle. So a lot of this HEM software and the software or principles of high efficiency machining are taking in chip thinning. That's what they're doing. They're taking in your light radials, heavy axials, but what they're really trying to control is your angle of engagement. The higher the angle of engagement, which is, if you look at this slide, the angle of the material or your end mill that's in your material, what is the angle of that? That's where your heat's coming from. That's where your chip evacuation is coming from. So the higher that angle of engagement, the less flutes you got to put in, number one, and the less axial you can actually run on the tool. So we want to reduce that angle of engagement. So you can see from left to right, we're at 90 degrees angle of engagement on the left. That right there scenario, I'm going to tell you 4 or 5 flutes and watch your axial, because you're going to have a bad problem managing your chips. As we reduce the angle of engagement, AE right there, you can see at 45 degrees, it gets much better. Look all the way on the right, that angle of engagement gets smaller. That's what we're controlling. There's certain HEM software out there that lets you even program by angle of engagement. You can actually put your angle of engagement in there. So what it'll do is create your toolpath based on that angle of engagement, because that's what's going to generate the heat. That's what's going to generate the fatigue. That's what's going to ruin your end mill. So we're trying to control that angle of engagement by using these principles of HEM. You can see we're going to get decreased deflection, right? We're not putting as much stress on the tool, longer tool life, higher MRRs, which we're going to talk about, material removal rates. Chip thinning, you're going to have chip thinning. Chip thinning is not a bad thing. We want chip thinning because we're going to feed it faster and we're going to get that chip up. And we know if we're going to feed it faster, we're going to get better MRR rates. Longer tool life, lower cycle times, but we're going to have more lines of code. So make sure that processing speed is all adequate. Let's take a look at angle of engagement as we run around curves and like a traditional tool path. When we take an end mill and we go into those corners, this kind of shows you what we were talking about a little bit. As we run into a corner, you might have programmed a 45-degree angle of engagement, which is ideal for that end mill. As you hit the corner, the angle of engagement goes up. As we run in a straight line, we're at ideal angle of engagement. And as we get on the outside, look what happens when we hit the outside of a curve. Angle of engagement gets smaller. So when the angle of engagement gets smaller, the chip gets smaller. Now we're bringing in other stuff we don't even want to deal with. Now we're bringing in chip thinning too small, and we're rubbing the end mill, and we're going to wear it out that way, and we're going to burn it up over when we get into the corner. So HEM is taking all these conditions and controlling that angle of engagement, you know, as far as how that's being managed. So we're managing all those forces. I like this slide up too. If anybody out there thread mills, think about this when you're thread milling, okay? Inside arc, outside arc, right? If you're doing an outside thread mill or an inside thread mill, the angle of engagement on an inside radius is going to be larger than it's going to be on an outside radius. So if you're using a thread mill on an inside hole, reduce your feeds and speeds from recommended if you haven't already calculated for that. If you're doing an outside, increase your speeds and feeds, you'll get better tool life. We can help you with that too as well, with some software and just expertise. Same thing here. If you look at the tool engagement angle and you're actually coming into a corner, less on the left scenario of the slide, this is a common problem right here on the left. This is what we all hear. This is the nightmare of traditional machining. This is it. You take an end mill, you run it into a corner, and if it doesn't break, high five everybody in the shop if it doesn't break. If it's squealing, you know you're probably successful. And when you see the lines all the way up and down it, you're trying to figure out how you can take those lines out with a finish pass. More desired or a better scenario is taking lighter bites at that corner, little ones where you're taking little bites, but you're still increasing that angle of engagement in there. Ideal situation, use an HEM toolpath, get a smaller tool, manage your radiuses on the corner with the software that you're using, with the diameter of the tool, control the angle of engagement on the tool, control that angle of engagement, optimal tool life, best MRR you're going to get. And guess what? Guess what, folks? Smaller tool, less price of carbide. I'm going to tell you right here from working with Harvey Performance and working with any other vendor out there, the majority of the cost of the cutting tool is in the carbide. It's in the carbide. Carbide costs money. So if we can reduce the cost of the end mill or the diameter of the end mill, we reduce the cost of the end mill. So it's really trying to find out the right diameter for the right tool path. Now, I get this question all the time, so I'm going to jump into it because I know everybody's on the other end of the call going, yeah, but what diameter should I use? What's optimal? How deep can I go? I'm going to tell you there's a sweet spot for HEM. Remember, we talked about axial depth of cut and radial depth of cut. Sweet spot for HEM is 1.5 to 2.5 times diameter. That's what I find is the sweet spot. If you're using some of our software, which by the way, here's a big plug, Machining Advisor Pro, one of the best speeds and feeds calculator in the industry. I'm not just saying that because I work for Harvey Performance. I truly believe it's great software. It calculates all this stuff, angle of engagement, chip thinning. What I'm telling you, when you're using that software, 1.5 to 2.5 times D on the tool is your sweet spot for HEM. What do I mean by that? If you want to run max and you want to, just, do the old macho thing and show off that end mill and remove as much material, your 2 times D is going to be where you can run max feeds and speeds. That's not saying you can't run 4 or 5 times diameter with HEM. That's the right way to run HEM is 4 or 5 times diameter. Understand, when you get over 2.5 times D, things change. They change. You need to adapt. And what I mean is you need to start adjusting those radial depths of cut, those feeds, those speeds, and everything else. Just a little tip. I like to throw them in there because I know these questions come up, and that's what I would be asking. You show us how to use it, Don, but what is ideal for that? And we can help a little bit further with diameters and stuff like that. So let's talk about metal removal rate. I love using this slide because this has a lot to do with high efficiency machining. We measure our efficiencies at the spindle by how much material we are removing off of that block and how quickly we can do it. So when you're understanding material removal rate, it's measured by how many cubic inches of material we're removing a minute. Folks, this is an easy calculation for you to figure out. When I walk into a shop and I'm trying to do efficiencies at the shop, I'll tell you what, even if the customer doesn't let me know this up front, I will calculate MRR for I can recalculate it when I employ some of these techniques to show an improvement. So understand it's the how many cubic inches of material we're removing per minute. This is measured by taking your axial depth of cut, which is your vertical, your Z depth, times your radial depth of cut, your step over on the left or in your X or Y, times your inch per minute. Okay, you multiply those three, it's going to tell you how many cubic inches of material I'm removing per minute. Now, why do I like to bring this up with HEM? There is a trick to HEM, and I'm going to let you all in on it, and I'm giving some trade secrets, and this is great, and I'm sure you guys won't tell anybody, but I'm going to tell you guys just because you joined us on this, okay? A trick to HEM, if you're running that, and you say, let's say you want to get 10 cubic inches of material, that's your goal, or you have something that you want for cycle time or quoted time. If you are struggling with tool life and you are struggling with getting this to work, you have 3 things to work with. I call it the MRR triangle, right? Fire triangle, those kind of Bermuda triangle. It's not the Bermuda triangle, but it's a triangle. You have those three things at the pin. You have radial depth of cut, you have axial depth of cut, and you have inches per minute. So what I'm saying by that, let's say the end mill just doesn't sound good. It's not working. It's just chattering. It's not working right. You can adjust your radial depth of cut. Back off your radial depth of cut, okay? But because you backed off your radial depth of cut, your MRR went down. But guess what? We backed off the radial. Now we have chip thinning, more chip thinning, right? It's based on your radial. So now I can increase my inches per minute. So I'm trying to eliminate my trouble spots, whether it be my axial, whether it be my radial, or whether it be my feed. Any three of those you can adjust. So don't get discouraged when you're running an HEM toolpath. Look at these three things, the radial, axial, and inch per minute, and play with these. Call us, ask us, we'll make recommendations. Could be choking out because you have too much radial. We can back that off. Axial might be too high, but then we back off the axial. But guess what? We increase the radial because that changes things with your chip. So these three things you can adjust. Very important to actually run through that. Let's just look at this really quick here because I want to close up and get things open here for a couple of questions. But if you look at this MRR situation here, it kind of shows you that if you go 2 times D, that's 2 times D axial, but only 4% radial, your MRR calculated is 4.83 cubes. That means you're removing 4.83 cubic inches of material per minute. Let's just skip all the middle stuff, go all the way to the right, which is traditional machining. Now we're taking a heavy radial, 40%. We're mowing, right? It sounds like we're removing a lot of material, but we're only going quarter times D. Our cubes drop down to 0.488 cubes. Now, which one are you thinking is going to be optimal for your situation? Not only are we reducing the cubes by doing that, we're bringing heat, vibration, and everything else, and chip evacuation as a huge issue too as well. So let's talk about qualifying an HEM. We're going to close with this and then open it up. So let's qualify these things. Key questions you need to ask yourself. Is this right for you, right? Is your tool holding optimal? Do you have that right TIR? Do you have the right tool holding? Is that optimal? Am I using the right stuff? What should that be for my situation? Are your part holding conditions ideal in the fixturing and all that? Do I have ideal holding and everything, which means can I use the whole axial? Can I get over toe clamps and stuff like that? Is your spindle condition in good shape? Nobody's ever crashed a machine. I'm got my fingers crossed here. I've never crashed a machine. Never broken an mill either. I don't know if I told you at the beginning, but never done that. But is your spindle condition in good shape? How many crashes on the machine? What's it look like? What's the TIR? Does your shop culture fit this new methodology? Will they embrace change? This is important. I can tell you, anybody that's not using HEM right now, just walk to a shop, get a buddy, go online, whatever, ask them if they use HEM. If they do, ask them if it's working for them. This is something that sometimes is a little bit hard to get over because we always have that mindset, hey, we've been doing it this way forever, right? I'm telling you, if you're not embracing HEM, it's time to take a look at this. And if you have new, younger people in your shop, ask them. Because I guarantee you, they're the ones that are on YouTube and they're the ones looking at this stuff and they're the ones playing with the software. So if you have younger people working, if there's some owners here working in their shops, just walk up to them and go, hey, have you ever heard of this HEM or high efficiency machining? And just let them run with it. Trust me, you will be glad you did. Are you willing at looking at reducing your tool diameters? That's a great question, isn't it? Yeah, nobody's looking at reducing tool diameters. Do you have a cam package that can or will support HEM? Do you have the master cams, the Esprit? Most cam packages support this. Shouldn't be an issue. Do you know your material exactly? This is a big one. Do you know the certs? What's the hardness? What's the Rockwell? Because this is really going to be conducive to what should I take for a radial? What should I take for an axial? And how fast can I run that? It's important to understand that. Are you roughing enough material? Listen, I get it. I'm the first one. You're doing a prototype. You want to hog out some material. Grab an end mill, run a full slot, go through it. That's fine. It's understandable. We all do it. There are places. If you have a production run, you're roughing enough material, might be a good situation to look at HEM, high efficiency machining. We can help with that. If you're new to it and you want somebody to support you and help. Listen, I know we're all kind of cooped up a little bit here. We have no problem working with anybody on that. We have qualified application engineers all over the country that can support. So first thing, summary. We're just going to summarize here and then go into questions. What is HEM? I'm going to ask that question, let everybody answer real quick. What is HEM? Okay, so I'm sure everybody said it's helical end mills, right? Yeah, right. Now, Harvey end mills, it's not. It's high efficiency machining. Very important. High efficiency. So you could call it helical end mills. What were the 3 T's, right? Those are the critical things. Tool path, tooling, technique. Make sure you have the right tool path. Make sure you grab the right tooling. Make sure you use the right technique. What is chip thinning, TEA, MRR? Chip thinning, we understand what that is. Chip's going to get thinner. Let's feed it faster. TEA, tool engagement angle. We are controlling that. Your software is controlling that. MRR, material removal rate. And then how to qualify your application for HEM. Listen, I'm trying to close up here really quick. There's so much more to this I wish I could share with you guys. Hopefully there's some good questions. I'm going to turn it over to Jeff. I appreciate your time. Thanks for listening.
All right. Yep. Thank you, Don. Yeah, so we had a lot of really good questions. So I'm gonna throw a few at you here. First one was there were some questions about Machining Advisor Pro and the parameters that outputs versus just general parameters and how we kind of you'll get different chip loads and different numbers based on the two. If you could just talk to the differences between, our published standard speeds and feeds and what you can get in Machining Advisor.
Yeah, so I'll go over it in the Machining Advisor Pro. I'm gonna throw this out to everybody right now. I am recording a video right now that walks through all that we will be launching. I don't know if it'll be on our webpage or if Jeff will do something differently, but I'm going to walk through a demo just like this. We're gonna walk through Machining Advisor Pro. But to answer those questions really quick, it is all on the toolpath. You'll notice in Machining Advisor Pro, you get to pick options: traditional roughing, high efficiency machining, okay, that's in there. Finishing, slotting, okay? So your chip loads are gonna be based on what tool path you pick first of all. Now that chip thinning I talked about, the Machining Advisor Pro takes in account chip thinning. So when it's changing the surface foot, when it's changing the chip loads, it's taking in account chip thinning. So it's an intelligent software, but there are things with it and nuances and tips and tricks that I think I can help educate people out there a little bit better. Look for that to come out in the next week. Hopefully that answers your question, but I'll try and answer more in a separate video.
Awesome. Well, looking forward to that one. We'll share that out so everybody has that. So another question that came in was about CAM softwares, Fusion 360 and Mastercam were mentioned, and so they asked for a radial engagement as a measurement of length versus a tool engagement angle, and just kind of people were wondering why we kind of talk about the tool engagement angle when in their software, it's asking for that measurement instead.
Yeah, so this is an easy one. So even though you don't know it, what these softwares are doing are controlling that angle of engagement. So all software does HEM a little bit different. Fusion 360 is adaptive clearing. Mastercam is dynamic milling. Esprit is profit milling. So they're all doing different things. But what they're doing is they're trying to control 3 things. They're trying to control the angle of engagement. They're trying to control the radial step over for heat. And they're trying to control the feeds. So all of them do things different. What some will do is as they come into a corner, in order to control the angle of engagement, if you program a 30 thou radial step over, it will automatically back off the radial step over in the corner. You don't see it, but I'm telling you, pull up the toolpath, open it up in some software, and you'll see the radial engagement angle gets less on the software. It's doing it behind the scenes. That's what they're doing to try and control that. So they're going to ask you what that radial step over is on that software. You're going to put it in, and then because the software is so intelligent and you don't have to worry about it, that's the great thing about CAM software. You don't have to worry about it. It's doing everything behind the scenes to control that angle of engagement, whereas profit milling, which is Esprit, has the angle of engagement. They're just kind of doing that up front. I'm not sure, and don't quote me on this, if there's patent stuff on that, and that's why everybody does it a little bit differently. But they're all trying to control the heat at the cutting edge to give tool life and stabilize. They're just doing it differently by feed, radial engagement, or radial step over.
Awesome. So one more question, kind of similar, talking about radial depths of cut. Are there recommended radial depths of cut that you would give to people for these high efficiency tool paths?
Yeah, so I'll give you a little tip and trick that I like to do. And this actually came, I'm going to give a shout out to Brian Stanger, who hopefully is on here and hears it. So I was actually working with him one day, and he came up with a pretty good general purpose solution for radial step over. It's almost like if you're using a 7 or a 6/5 or a 7 flute, a 6 flute, or a 5 flute, you can use as a general and mild steels or alloy steels. Just go 7 times 1, okay, 6 times 2, and then 5 times 3. So 7 times 1%. So 7 times 1. So for a 7 flute would be a 7% step over. For a 6 flute times 2 would be a 12% step over. For a 5 flute times 3 would be a 15% step over. So that's kind of a general purpose, but it all depends on your material. But you could do 7 times 1, 6 times 2, and then 5 times 3 is a good place to start. So 15% on a 5 flute, 12% on a 6 flute, depending on what you're doing and what material, and then 1% on a 7 flute. It's a good starting point, but that's also conducive or directly related to what your axial is, what your diameter, and your times D. So there's more of a science behind it, but those are good places to start.
Cool. And yeah, there's a lot of variables, I'm sure. So if anybody had more specifics, definitely reach out to us. We'll try to figure that out for you. So a couple
No, we won't.
questions.
We won't try, Jeff. We'll figure it out.
We'll definitely figure it out. So a couple questions just came in. Do you think HEM techniques are applicable to milling marble and granite? I don't know how much experience you have with that, but if you could talk a little bit, we had one person asking about those materials.
Well, marble and granite's going to be abrasive, okay? Coating, tool geometries have a little bit more to that, but anytime you can reduce the load, and marble and granite, it's going to be a little bit like exotic. And the biggest thing with HEM techniques is to stabilize the cutter, right? So marble and granite are going to push back. They're going to push back on the cutting tool. So although I haven't done it, I haven't cut marble and granite with HEM techniques. The technique is all to reduce the load on the cutting tool. So I do not see why it would not be beneficial for those materials, 100%.
Cool. One interesting question just came in. Do you have a few strategies for getting guys in your shop on board with these concepts?
Yeah, keep picking away. Keep picking away. It's like the kid that wants to go to the park and the parents don't want to go. I mean, he just keeps asking and asking and asking. Show videos. The big thing is from my experience, and I've been doing this for 32 years, and first of all, respect the guys around you. Don't shove it down their throats. But I'm telling you, just keep showing videos, bring in examples. A lot of the older school guys, this is where it's changing, right? Because we have this mindset in the cutting tool industry, and I have the opposite. And the mindset is, oh man, we better be careful because we're losing all this old school experience. We're losing all this. What are we going to do when all this old school experience leaves? Well, guess what? The young kids and the ones that are in these technical colleges and the ones coming out of these programs are learning these new techniques. So if they can understand the cutting tool end of it, this is where we're going to thrive in the machining industry. And this is where everybody out there in public speaking and on YouTube are really helping the industry with these new techniques, because it's the younger generation that's coming in. So I would just say keep plugging away, keep picking away. We can support you in that. We have presentations. Share these presentations with other people at the shop, and hopefully they change their mindset. And if
Great.
they don't, punch them.
There you go. So a couple questions I can actually answer, which surprised me. But I've got a few. Is Machining Advisor Pro going to include Harvey tool instead of just helical at some point? I mean, the answer is yes, at some point. There's a lot of stuff that goes into that. And obviously, with many more tools and tool styles and a lot more materials to consider, there's a lot of work that's going into that. But at some point in time, yes, it's just a big undertaking, but that is the goal. And then I guess, Don, you can answer this, but can I use the same concepts of HEM and aluminum?
100%. I
100%,
love this.
right?
Yep. So here's the thing in aluminum. So remember we talked about the radial step over? I'm going to tell you right now, grab yourself a 3-flute, an H35C. It's a new tool that we just launched. It's a chip breaker 3-flute, H35. You take that axial depth, you bury that thing all the way down. You go 30, 40% with that tool, depending on your machine, Okay. I say this because I don't know your machine, but I'm telling you that tool will run 60, 600 inches a minute all day long. MRRs is 75, 100 cubes, depending on diameter.
And so, do you have any like recommended step overs for the 4, 3, 2 flute cutters, similar to the 5, 6, 7? People are asking about that, just in
Recommended
general.
step over for the in HEM, a 2-flute tool. So a 2-flute tool, I would go about 40% step over. Ideal HEM in aluminum, my opinion, is 30% step over. I like 30% step over in aluminum with a 3-flute. I would say 40 to 50. 50 is kind of pushing it. You're starting to change a little bit of geometry on the end mill. Easily can do it, but we're going to run fast enough at 40% with a 2-flute step over that you're going to forget about 50, 60, 70%. You'll max out your machine.
Awesome. So I think that, unless there's any questions last minute here that come in, I think that covers most of them. I will say, sounds like we have a class from Lincoln Tech in Connecticut.
Right,
Mr.
shout out.
Mr. Feliciano here said he has his class on this call, CNC machining class from Lincoln Tech, so that's pretty cool. So shout out to those
Shout out to
guys.
Lincoln Tech.
But yeah, I think that's about it for this one. So just want to thank everyone for tuning in. We will follow up with a recording. Anyone who registered for this, you'll get an email with the recording. It'll also go public on this YouTube page so you can watch it later. And hopefully you join us again next week. We have a few more of these coming up, like Don said, on micro machining, exotic materials, and then hopefully diving into some turning and micro 100, maybe some Swiss machining. So lots of good topics to cover in the next few weeks. So keep an eye out for emails on those. And that's about it for us. Don, if you want to just.
Yes, I want to say thanks for everybody joining. I know these are some rough times, so hopefully we can bring a little bit of education. We're going to get back out there very soon, and we're going to start crushing some material.
All right. So
thank you.
Everyone have a great rest of your day. We'll talk to you next week.